All right, good morning, everybody. As Bill said, my name is John Lewis with the Virginia Institute of Marine Science Eastern Shore Lab, and today I'd like to talk to you about my graduate research I conducted at the Auburn University Shellfish Lab on the effect of wave action, biofouling control, and density on the performance of eastern oysters in an off-bottom system. So I'd like to provide a little context for the word performance that we're using in this presentation today. Across all general oyster aquaculture, on bottom or off bottom, it's mostly a combination of two main quantity metrics of survival and growth, which provides a farm its yield. However, off bottom oyster performance on farm sites throughout the Gulf of Mexico and the East Coast may also include other quality metrics such as oyster cleanliness, oyster meat condition, shell shape, and product consistency. There are a multitude of factors that can affect oyster performance in an off-bottom system, the first of which come within the physical environment. As many of you are aware, salinity and temperature have a major influence on the product that you can produce on your farm. So for salinity, oysters are said to thrive in salinities greater than or equal to 20 parts per thousand. However, this can be region dependent. Salinity also significantly affects the taste of oysters from a given site, as many of you are well aware as well. And dermo-infection is prevalent at greater than or equal to 15 parts per thousand in areas where dermo is present. For temperature, the best growth is said to be between 10 to 30 degrees Celsius or 50 to 86 degrees Fahrenheit. So with this in mind, doing my research in the Gulf of Mexico, I thought it was important to point out that the Gulf of Mexico does provide or typically provide year-round or near year-round optimal growth conditions for temperature. And this faster growth or lengthened growing season can actually have a reduction of disease impact since the oysters are harvested before that disease can cause any major mortality events. And then other attributes of the farm site that Brendan touched on, some including flow that can bring in new food and renewed dissolved oxygen to the site can have an effect on oyster performance. The other set of factors that can affect oyster performance come in the package of the culture practices chosen by the farmers. So the choice of a floating bag or a floating cage versus a long line system, a suspended system, can have a significant impact on your oyster performance. There's also the ploidy or genetic of your stock of oysters on your farm. So triploid oysters have been shown to grow faster than their diploid counterparts. However, there have been unpredictable mortality events reported in the Gulf of Mexico, specifically in those triploid stocks. And selective breeding has been attempted in the past for accelerated growth and disease resistance, so either of these ploidy or genetic lines, if available from your hatchery, can have an impact on your oyster performance on your farm. And then other things that farmers can manipulate include stocking density, biofouling control regimes, or mechanical tumbling and sorting, which can have an effect on oyster performance. But we wanted to nail down what is the effect of wave action at a given site. This has been referred to in a few studies as possibly impactful to oyster performance. However, few studies have focused on that explicit impact of wave action on a given farm site. So for our experiment, we utilized the adjustable longline system. We had 12 unique treatment combinations with 8 replicates of each for 96 baskets total. This filled up one entire longline run. But we did have the total loss of one treatment prior to the completion of the experiment, so all of my results you'll see later only have 11 of the 12 unique treatment combinations present. Each unique treatment combination was a combination of 2 wave action, 3 biofouling control, and 2 density treatments. So for wave action, we had weighted or dampened wave action treatments where the basket had a 5-pound section of rebar attached to the bottom to act as a weight. And then the unweighted baskets were our natural wave action treatment. Our 3 biofouling control regimes were weekly desiccation at 24-hour duration, fully submerged for the entirety of the experiment, and power washed on an as-needed basis. And then we had 2 density treatments, with low density being 50 oysters final stocking density and high being 100 oysters final stocking density. We used one site out here at the Mississippi DMR Commercial Aquaculture Park near Deer Island for this experiment. This site was selected for the frequency of high wave action that's commonly experienced at this site. And in addition to providing the site, environmental data was also provided by Mississippi DMR and is shown in the graph here on the right of the slide, with mean daily salinity in red dots and mean daily water temperature in the blue dots. Our experimental triploid oysters were deployed on July 30th, 2020 in 6mm BST baskets. They were given 1 month to acclimate to the site and then sampled. So 1 month after deployment, oysters were set to their final densities of either 50 or 100 and transferred up to those 12mm BST baskets in which they would remain for the rest of the experiment. Our sampling occurred every 6 weeks after sample 1 for shell dimensions and survival. And shell dimensions are shown here on the right of the slide, where shell height is the distance from the hinge to the bill. Shell length is the widest measurement perpendicular to height, and shell width is the widest measurement from valve to valve. Our final sampling took place on March 2nd, 2021, about 8 months after our deployment, with 15 oysters from each basket retained for lab processing, final live dead counts, and then photographs of basket fouling were taken. During our final sample processing, condition index was completed. So this process starts with timing how long it takes to remove all fouling from every oyster through scrubbing and scraping. Shell dimensions are then measured as previously described, and then the whole wet weight is taken for each oyster. After the wet weight is taken, all oysters are shucked, all tissue removed from the shells, and each are dried and subsequently weighed and placed into the equation present on the slide for a quantification of meat condition. In addition to this, survival was analyzed, and then we analyzed basket fouling. However, I'm not going to talk about basket fouling today to save a little bit of time. So moving into our first response variables, we have our production quantity variables of survival, shell height, and whole wet weight. And before diving into these results, I'd like to explain a few things about the upcoming graphs. So first, treatments are broken into 2 main groups, with natural wave action to the left of the dotted line, reduced wave action to the right of the dotted line, and labeled as they are. Our different colors represent biofouling control treatments. So green is our weekly desiccation, red is our submerged for the entirety of the experiment, and blue is power washed on an as-needed basis. And then hopefully that comes across out there, there's a lighter shade of each color and a darker shade of each color. So the lighter shade is low density and the darker shade is high density. Bars that share a letter on all of these graphs are not statistically significant, and 95% confidence was used throughout our analysis. So for our first response variable, survival throughout this study was high overall, and we did not observe any large mortality events in the 8 months that these oysters were in the water. So due to this high survival, there were very few significant differences present between our treatments. But with that being said, our high density power wash treatments, or the dark blue bars, tended to have lower survival in comparison with the other treatments. Shell height on the left and whole wet weight on the right were analyzed as our main metrics of overall growth. And as you can see, results from each really nearly mirrored one another, where natural wave action generally led to a reduction in growth when compared to reduced wave action. Increased density tended to significantly increase shell height. However, this pattern was not as clear for whole wet weight, and there was no distinct effect of biofouling control. However, it is important to note that the submerged treatments in the reduced wave action group, so the red bars to the right of the dotted line, produced the significantly largest oysters in both shell height and whole wet weight. Moving on to our production quality metrics, we have cup and fan ratio, condition index, and cleaning time. So our oysters within this study really excelled in terms of cup and fan ratios, producing averages well above the industry standard of 0.25 cup and 0.63 fan ratio. But in contrast to shell height and wet weight, we saw the opposite relationship between wave action and cup ratio, which is here on the left of the slide. Fan ratio is on the right of the slide. Natural wave action produced the highest cup ratios in this case, with reduced wave action leading to a reduction in cup ratio. In general, low density tended to increase cup ratio relative to high density while holding the other treatments constant. However, this pattern was not significant across the board, and biofouling control provided no distinct pattern for cup ratio. Fan ratio, on the other hand, produced no consistent differences across treatment combinations, and neither natural or dampened wave action seemed to provide any advantage. Low density only produced significant increases of fan ratio between desiccated and submerged treatments, within the weighted wave action group, so there were very few differences present. We think the lack of consistent patterns for fan ratio is likely due to the overall high values that are already present across treatments, and then the little absolute difference between the smallest and largest averages. For condition index, high values were again observed, and we attribute these overall high values to the overarching impact that off-bottom culture and triploidy have on farmed oysters, which have both been shown to significantly increase condition. In this case, however, wave action played a less significant role, as there were few significant differences observed between natural and weighted treatments, holding all the others constant. Low density significantly increased oyster condition or meat condition in a few cases while holding other treatments constant. However, this pattern was not consistent across the board, and desiccated treatments tended to have high condition, but our submerged treatments were comparable in all cases but one. The most obvious impact here is that of power washing, which seemed to have an overall negative effect on oyster meat condition. For the final metric of oyster quality, cleaning time was analyzed. So our weighted treatments took significantly longer than natural wave action treatments in all cases aside from the high density power wash treatments, which were essentially equal. While this wave action pattern was present, cleaning time was mainly dictated by biofouling control, as would be expected. Desiccated treatments took significantly shorter to clean than all other treatments, and submerged treatments within the weighted wave action group took the longest, as you can see by the red bars to the right of the dotted line. Low density led to a general reduction in cleaning time. However, this pattern again was not significant across the board. So in general, higher wave action tended to increase metrics associated with quality, but reduce the metrics associated with quantity. However, we did see some interactions that were present between our treatment categories. So our following recommendations are really generalizations based upon the results presented here. So for a farmer intent on maximizing quantity, or just solely survival and overall growth, in a low wave environment should consider a lower stocking density and no biofouling control. A farmer intent on maximizing quantity in a high wave action environment could consider increasing their stocking density and power washing. A farmer intent on maximizing quality across the board, regardless of wave action, should consider a lower stocking density and weekly desiccation. And strategies to find the best compromise between our quantity and quality trade-offs really depend on wave action at a given study site or farm site. So in a low wave environment, farmers looking for a good compromise should consider increased stocking density and weekly desiccation, although you'll have to deal with a relative reduction in your fan ratio. And in a high wave environment should consider an increased stocking density and no biofouling control, although this will lead to a significant increase in oyster fouling. And a few thank yous before I step off stage. Huge thanks to Dr. Walton for letting me do the research that I'm super interested in and for mentoring me throughout the whole process. Big thanks to Dr. Sturry and Dr. Gray for being on my committee and helping me throughout the writing process of my thesis and the analyzation. I can't say thanks enough to the Mississippi DMR folks, everybody listed here and everyone else who helped. This wouldn't have been possible without their site and their environmental data and boat trips and manpower and everything. So a huge thank you to all those folks at Mississippi DMR. And then of course, thanks a bunch to my Auburn University Shellfish Lab family. Again, none of this would have been possible without any of the people listed here. And with that, I'll take any questions.
We have a question over there.
Okay, Andy.
So the proximity to the surface seems to make a lot of difference. Did you look at were your oysters desiccating intertidally on low tide?
So we would actually go out and physically move the baskets. The way we set this up, and let's see if I can go back to the diagram here. We actually set an extra line on the long line system. So one line was static under the water surface, and then another line was set static at the very highest possible setting. So those baskets were actually physically removed from the bottom line and placed on the top line during desiccation. And the same is true for power washing. We would lift them up, power wash them, and then put them back down. The submerged baskets stayed underwater for the majority of the experiment, other than super crazy low tides where even the lowest setting, there was only 2 foot of water out there at the site.
But you didn't suspend one group high and another group low?
No, sir.
Okay.
They were all relatively static on that bottom line with a little bit of give for, there might have been some sagging in some areas of the line.
A lot of people using that gear now are setting it so they do desiccate intertidally, and they get a lot more wave action than they do when you pull them up and desiccate them weakly and everything. I was curious how that was working, but that's okay. Thanks. Good job.
Thank you.
All right, got a question over here?
Thank you for the study. Is there any metric that guided you in determining the stocking densities of 50 and 100? And what gear were you guys using for the baskets?
So
Thank you.
for the gear, we utilized the BST baskets, just regular 6 mil and 12 mil BST baskets on the long line system out here. For density, we really just kind of threw those numbers out there. They seemed like common stocking densities that farmers tend to use when they use a long line system with 100. At the end of the experiment, some of the baskets were chock full. There was no oyster movement at the very end. We concluded it when oysters made it to that 3-inch range. So the oysters stocked at 100 per basket actually were almost outgrowing the bag by that point. So we figured that was just a good common stocking density. We had the 12 millimeter baskets is our main experimental basket, and then we also utilized 6 millimeters, but that was only for a short amount of time.